Welcome to our discussion on derivatives of polynomials and exponential functions, basically taking derivatives of powers of x, and then we'll also look at numbers to the power of x, 2 to the x, 3 to the x, e to the x, those types of things. So it's going to be all about powers today. Let's start by looking at the constant function, f of x equals c, right, which you can think of as just a horizontal line at a height of c. So we just think of it as y equals c. Horizontal lines we know all have a slope of 0. And so therefore if we take the derivative of that function, we're actually asking for the slope of its tangent line. And since it's a straight line, the tangent line is the line itself, right? And we end up getting that the derivative has a slope of 0. So we now know that the derivative of a constant is 0. Now you can run through the formal proof if you want to, right? Because if you try and do f of x plus h of a constant function, you just still get c because there's no x to plug an x plus h in. And then f of x is still also c. You get c minus c, which is 0. 0 over h is 0. And then when you take the limit as h goes to 0 of 0, it's just 0. So there you have it, right? The derivative of a constant is 0. Very important. It's going to help you out a lot when you're starting to take derivatives of things, especially when we want to take derivatives of polynomials. Next one we can look at is a straight line that doesn't have a slope of 0, so any other straight line. In this case we can look at the simplest one of just y equals x. And of course y equals x, the tangent line will be the same thing as the line, just like it would be for any straight line. And we know that the function y equals x has a slope of 1. And so therefore if you take the derivative of y equals x, you will get a derivative of 1 as well. Which leads us to our next revelation that the derivative of x is equal to 1. Now we've already seen from previous investigations, examples and whatnot, that the derivative of x squared was 2x and the derivative of x cubed was 3x squared. So now we can move on and look at what happens when we take the derivative of x to the fourth. Well, you can follow along with all of this messy algebra, right? You got to plug x plus h into the function, which means you have to raise it to the power of 4, which means you're going to have to FOIL it over and over and over again, combine all your like terms, simplify it on down. You finally get things all in terms of h, so you can finally do the division and get rid of the h. Now you take the limit as h goes to 0, which means all of the pieces that still have h's in them all go away, and you're left with 4x cubed. Okay, so we had the derivative of a constant, which is really the same thing as x to the 0, right, equals 0. We had the derivative of x, which is the same thing as x to the 1, equals 1. We have the derivative of x squared equals 2x. The derivative of x cubed equals 3x squared. And then now finally the derivative of x to the fourth equals 4x cubed. Do you want to hazard to take a guess what you think the derivative of x to the power of n is going to equal? If the pattern holds, right, look what's happening. Every single time the power comes down in front and then goes down by 1. So 4 times x cubed, 3 times x squared, 2 times x to the 1, 1 times x to the 0, and then 0 times x to the negative 1, right? But 0 times that is just 0. So the pattern holds and you get n times x to the n minus 1. And there it is in all of its official glory, right? This is your first shortcut rule that's going to help you to take derivatives of various things. Because now that you can take the derivative of x to a power, you should be able to take a derivative of all polynomials. How about some examples, right? X to the sixth, very simply, 6x to the fifth, x to the 1,000th, right? T to the fourth. Oh, hey, so it works for other variables? Yes, it works for all variables, right? It's all the same thing. And of course, derivative of r cubed. Just please be aware that when you're taking the derivative of t to the fourth, you have to be taking dy dt, which means you're taking the derivative of y with respect to t now, because if you were taking it with respect to x, this wouldn't change because it's not an x and it's not changing, right? It's how fast is the function changing with respect to a change in x. Well, if you were looking at this function, you said, well, now if I let x change, what happens to the function? Function stays the same, nothing changes. If x doesn't change, then the t to the fourth isn't giving you different outputs, right? So that's what the respect to is important here, the derivative with respect to r. If you did a ddx of r cubed, it would just be 0, right? Because r cubed would now be considered a constant. Okay, so we can generalize the power rule. The derivative of x to the n is n times x to the n minus 1. We've already seen this, but the nice thing about the power rule is it enables us to find these tangent lines without having to use the definition, which is also going to allow us to find what are called normal lines. If you've never heard of a normal line before, a normal line to a curve is just a line that goes through the point P, right? So you always talk about a normal line to a curve at a particular point. So at some point P, the tangent line, of course, touches in one spot and has that tangent property to it. The normal line goes through that same singular point P, but it's perpendicular to the tangent line. So if we can use this formula, remember, to find the derivative, which is the slope of the tangent line, at a certain point P, so you can plug that P in and get the actual numerical slope of that tangent line, then all you have to remember is that the slope of a perpendicular line, right, is just minus 1 over the other slope, right? Opposite reciprocals. So whatever m was, if you want to find the perpendicular m, you flip the fraction and multiply by -1. Okay, other things to help us out in our journey of trying to take all these different derivatives is if we create new functions from old functions using addition, subtraction, or multiplication by a constant, all of those new things, i.e. kind of simple polynomials, can be found very simply by using the idea of the derivative of a constant and the constant multiplication rule, which really derives itself from our limit. Remember the rule of taking the limit of a constant times a function was the same thing as a constant times the limit of the function? I'll write that down to remind you. If we're taking the limit, right, as x goes to a of some constant times f of x, that's the same thing as the constant times the limit of f of x as x goes to a. Remember that rule? Well, since derivatives are really limits, remember by the definition, it's the limit as h goes to 0, but that's the same thing as x going to a. If we can take the constant out of a limit, we can also take the constant out of a derivative, and that's where we get the constant multiple rule. So the derivative of a constant times a function is the same thing as a constant times the derivative of the function. So now, if we're trying to take the derivative of 7x to the fifth, you go, well, that's just 7 times the derivative of x to the fifth, and of course the derivative of x to the fifth is just 5x to the fourth, right? And then 7 times that, and you now have 35x to the fourth. Done, easy, simple. Here's some other examples. You can look through those and see that it's relatively straightforward. So let's move on to the sum rule. So if you have these two functions f and g, they're both differentiable, then the derivative of the sum is the sum of the derivatives, just like how the limit of the sum was the sum of the limits. Right? Comes from the same idea. And then of course we can expand that to 3 and 4 and 5 and as many functions as we want. Same thing is going to go for subtraction, right? What we call the difference rule. And again, we can do it for multiple functions, not just 2. You can try to compute the derivative of the exponential function a to the x using the definition of the derivative if you want. So far we've seen we can take the derivative of a power of x, we can take a derivative of a constant times the power of x, and then we can take a derivative of sums and products, sums and differences of functions, and everything is nice and easy. The next thing we're going to try and do is think about, well, how about a different power? Instead of x to a power, now I want a to the x, where a can be any number. Well, if you use the simple definition, take the function and evaluate it at x plus h, you get a to the x plus h, but then by the rules of exponents, that's just a to the x times a to the h. And then when you also have f of x, which is just a to the x, you can see at this step that you have both pieces times a to the x. So then you factor it out, and you're left with a to the h minus 1 all over h. Well, since this definition is talking about the limit as h goes to 0, and there is no h in this, I mean, technically what's happening is we're doing the limit of a product is the product of the limits, right? And we end up getting the limit of a to the x times the limit of this other piece right over h. But remember how we talked about we had the limit rule for the limit of a constant was just that constant. Well, yes, a to the x isn't a constant, but it is when you're letting h go to 0, right? The only thing that's moving is h, and there's no h in this, so it's considered a constant. And that's why it just comes out here. And it looks like, oh, it's just magic. You just pulled it out of the limit. And, well, what we really did is we pulled a constant out of the limit. It just so happens that constant has an x in it, and the reason why it's a constant is because it doesn't have any h's in it. Okay, so we've got that piece, and then the leftover piece, which does have h's left in it. So now we have to look at that piece. I love it when books do this. They just tell you to notice something, or they say like the proof is left up to the reader, as if we're supposed to just look at this and go, oh yeah, of course I see that. That's the derivative at 0. All right, let me show you a little bit of where they're coming with this. If you'll recall, the derivative of a function at a particular point a, right, is equal to the limit as h approaches 0 of f of a plus h minus f of a all over h. Okay, and then remember we're dealing with the original function, f of x is a to the x. It gets a little confusing with the two a's. These are two different a's, right? This is just at some point, and then this function is talking about a particular base number. Okay, if we're going to claim that this is the derivative at 0, then that just means a equals 0. And if a equals 0, we're now saying the derivative, right, at 0 is the limit as h goes to 0 of f of 0 plus h minus f of 0 all over h. F of 0 plus h is really just f of h. So now we have f of h minus f of 0, which is a to the 0, and anything to the 0 is just a power of 1, and the bottom is still h. And ta-da! That's where it comes from. Okay? So it is true, right, that that piece is the derivative of the function at 0. So therefore we've shown that if this exponential function a to the x is differentiable at 0, then it's differentiable everywhere, and the derivative is equal to a to the x times its derivative evaluated at 0, because remember from the previous algebra, that's what we were left with, right? When we took the derivative using the definition, we were left with a to the x times this limit piece, and as we saw from the next slide, this thing here ends up equaling the derivative evaluated at 0. So this is telling us, this equation is telling us that the rate of change of any exponential function is proportional to the function itself, right? Because the derivative is the rate of change, how fast it's changing. So the speed at which this function is changing, its derivative, is just equal to the function itself times a constant, right? Times a number, and that number happens to be the derivative of the function at 0, but it's still a number. So that means the rate of change of the function is proportional, means that it's just itself times a number. That's what proportional means. Okay, we can do some investigation. We can kind of try and figure out, um, we're trying to prove that the existence of this f prime of 0 works everywhere. So we can try it with different bases. We can let a be 2 and then see what we get. Let a be 3 and see what we get. And when a equals 2, we get this f prime at 0 ends up being roughly 0.69. And when a is 3, we get that same derivative of f prime, at 0, ends up being somewhere around 1.1. And this is just letting your change in h, or sorry, your change in x, which is your h, right? Let your h get smaller and smaller and smaller. So you're taking those secant lines and you're getting closer and closer and closer to the tangent. Okay, so you're getting a slope of about 0.7 for when it's a 2 and a slope of about 1.1 when it's a 3. Well, the fact is, it can be proven that with these two, that these two limits exist, and that they're roughly these two numbers. And from that, we can basically, round even further, unfortunately, and say that the derivative of 2 to the x is roughly equivalent to this 0.69 times 2 to the x. The derivative of 3 to the x is roughly equivalent to 1.10, right? I would have rounded to, I don't know, 1.099 or something, but it depends on how many you want to go to, times 3 to the x. Now, of all the possible choices for the base a in these formulas, the simplest differentiation formula occurs when the derivative at 0 equals 1, right? These little numbers in the front, if they were just 1 instead of 0.69 or 1.1 or whatever else we get, that's going to be the simplest formula, because then the derivative is just going to equal itself, right? Think about it, if we just had the derivative of a to the x, it's going to equal some constant times a to the x. And if that constant was 1, then lo and behold, we get the derivative of a function equals itself. Well, we can see that because 2 was a little bit less and 3 was a little bit more than 1, it would seem reasonable that there should be a number between 2 and 3 such that the derivative evaluated at 0 equals 1, right? We're just kind of going from patterns. 2 gives us a number less than 1, 3 gives us a number greater than 1. So something in between the two. Well, it's been proven, right? But basically what happens is, by churning out numbers and lots and lots of computation, you can figure out what that number is between 2 and 3, and it ends up being this irrational number that has digits that just keep going on and on, very similar to pi. And we just gave it a special name. We called it e. So when you see that number e, and we all know that's 2.7 something 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 something, e is the number such that the limit as h goes to 0 of e to the h minus 1 over h equals 1. We've basically defined e as this limit. We found the number where this limit ends up giving us 1. Now, if you graph all those things, remember this whole derivative at 0 is just the slope of the tangent line at 0 when x equals 0. So each of these graphs over here on the left are going to have slopes going through that point. And you can see that they're going to be different, right? Depending on the blue one is going to have kind of a shallower slope, right? And then the red one gets a little steeper, and then the blue one gets the black one gets a little steeper, and so on and so forth. Well, the blue one has that perfect 45-degree angle slope, which is a slope of 1. So it's just kind of a graphical geometric proof that, or evidence that the slope of the tangent line at 0 does in fact equal 1 when the base is e. Which brings us to that kind of aha moment that we were talking about before, that now when we take the derivative, we get the derivative of e to the x is going to be that number out in front times e to the x, just like before it was that number times 2 to the x, or some number times 3 to the x. Well, that number ends up being 1, and so we get that this e function, e to the x, is its own derivative. It's a very powerful thing. That means that the slope of the tangent line to that function at any point, pick a point, any point, the slope of the tangent line at that point is equivalent to the function evaluated at that point. So e to the fifth, right, whatever that number is, that's the slope of the tangent line at x equals 5. It's pretty amazing. With that in mind, we can now start taking derivatives of polynomials that involve e. So we can take the derivative of e to the x minus x and see very simply that it's still just going to be e to the x, right? And then minus 1, because we have that rule, right? The difference rule that you're just taking the derivative of the individual pieces. We could take the second derivative, do it all over again. And we're now taking a derivative of a constant, and we just get e to the x. What would the third derivative be? Well, that would just be e to the x, right? Because we take the derivative of this, and we still get e to the x. And the fourth derivative, the fifth derivative, and the nth derivative would still be e to the x. So the nice thing about e to the x is it bottoms out, right? You can take derivatives of polynomials, and you'll keep getting different answers until you get to a constant, and then it becomes 0. And then the derivative of 0 is just always 0. But with e to the x, every time you take a derivative, you just get e to the x. So it never goes away. So the function f and its derivative f prime are graphed here. That was the original function we had, and then its derivative. You'll notice that the original function f has a horizontal tangent at x equals 0, right? If you put a tangent line here, it would be pretty flat, right? It'd be a slope of 0. This corresponds to the fact that the derivative f prime of 0 equals 0, and that's why the derivative function goes through the point 0, 0. You'll also notice that whenever x is greater than 0, right, we're out here in positive values, the original blue function is increasing. And because it's increasing, its derivative is positive, right, because it all has positive slopes. You see how these would all have positive tangent lines? But in the negative realm, the function is decreasing, right? It's getting smaller. And these are all negative slopes, and therefore the derivative is a negative number, and the derivative as a function, right, is below the x-axis. Okay, so the basics that we learned in this section is we can take derivatives of powers of x, we can take derivatives of a to the x, and then we can take derivatives of constants, and then we can take derivatives of combinations of all those things as long as it's a constant times something or other bits and pieces being added and subtracted together. Those are all easy, simple things to do.